All right, it's 1 o'clock. So this week in organic chemistry, we are going to be interpreting spectra, both carbon NMR spectra and hydrogen NMR spectra. Carbon NMR spectra is new as of today, but there's not a lot that you can do with it. It is unreasonable for anyone to be able to take a carbon NMR and figure out what the molecule is. I will not ask you to take a carbon NMR and tell me what the molecule is. You can tell little bits of information about the molecule, but I think it's a lot more like IR in that you can get little bits of information, but not a whole ton of them. Also, much like IR, it's really informative as to what's present as well as what's absent, but you can't go much farther than that. So let's go through this bridge. Did anybody have any questions in general about carbon NMR? Not really. So that is fine. So this bridge was really just one question of which could these possibly be. It's kind of a multiple choice question. Given this carbon NMR right here and these four molecules, which one fits? So that's the style of question that I would ask you, either multiple choice or true false of either does this fit or doesn't it, or which of these four fits best. But I gave you lots of little bitty questions because this is kind of how I think about it and how I break it down. So the first question really just is how many carbon NMR environments are there, which is very similar to hydrogen NMR environments, the main difference being we're looking at carbons instead of hydrogens. So Chloe, how do we do this? Yeah, how many do we have? Great, perfect, and that's it. So that information alone, if we look at these molecules, how many carbon environments are in this molecule, Timothy?
5.
How about this one?
Also 5?
Correct, how about this one?
5 as well.
What about this one?
4.
Yes. Hello.
I forgot I don't have a question.
No problem. So that one's right out, right? That's really all you can tell from that. So information, not a ton, but there's something. All right, so the rest of this is relating to the chemical shift of within carbon NMR. So I know that I gave you some more values to memorize if you'd like to, but I will tell you that I don't have those values memorized. I mostly break them down by kind of roughly where they appear on this chemical shift scale, which ends up being very similar to where they appear on the hydrogen NMR scale. The numbers aren't the same, but kind of where they are is about the same. So I'm going to tell you how I think about this, which might make your life a little bit easier, but I will ask you a bunch of questions. So what shows up farthest to the right on the hydrogen NMR scale? So 1 to 1.5, what shows up there? Yeah, so just kind of what functional group? So like alkanes, right? So the CHs that are just kind of on alkanes, not near anything, are the ones that appear farthest to the right. So what appears in the 2 to 2.5 region in a hydrogen NMR? You guys just had a quiz on this 2 days ago. It shouldn't be that far from your memory. Also, you need to be able to do it to do this week's stuff. So what appears 2 to 2.5? So CH is next to carbon-containing functional groups. So still not next to anything fancy. So with carbon NMR, we don't really differentiate those two things from each other. These are just kind of CHs that aren't right next to O's or N's or X's. So if we roll all of that in together, this is kind of our CH region right in here. It's the farthest to the right. I'm not, by the way, in case you try to sync this up with me saying that this is from -5 to 43, I'm just circling a general region. I'm not putting specific numbers on there right now. I'm just giving you a rough approximation. All right, so what came from like 30 to 60 in carbon NMR? Right, so carbons attached to halogens or nitrogens. And what was 60 to 90? Exactly. So what kind of came next here was those carbons next to O or N or X, if we group it all together. What appeared next in hydrogen NMR, so like 3 to 4 ppm. C, yeah, CH is next to O or N or X. So kind of the next region here, which I'm grouping a couple in together, but kind of your carbons next to O or N or X kind of appeared in that next rough region, which was like you had your kind of all the way to the right quartile, and then carbons next to O or N or X are kind of your middle right of the spectrum. So technically C next to N or X is like 30 to 60, and C next to O is about 60 to 90, but they're kind of all roughly in here. Does that make sense? So we're about halfway through. And they kind of follow about the same trend because de-shielding is de-shielding no matter who's being de-shielded. All right, so after that, we get to this kind of 100 to 150 region. And what shows up in this 100 to 150 region? All right, so these are, yeah, exactly. So this is carbons and C double bond Cs. Technically, triple bonds fall in the middle there, but triple bonds are far less common, so I'm just going to ignore those. You should not completely ignore those, but it's not the most common thing, so I'm not going to toss it on here. All right, so kind of this next quartile of the 0 to 150 is C double bond Cs. All right, so let's compare this to our hydrogen NMR again. So hydrogen NMR, 1 to 1.5 is just kind of alkanes. 2 to 2.5 is alkanes next to carbon-containing functional groups. So that's kind of the farthest to the right. And then that 3 to 4, which is middle right, is carbons next to O's or N's or X, or CH is next to O's or N's or X. So they kind of follow about the same trend. In carbon NMR, the next thing is carbon double bond carbon. So let's think about hydrogen NMR and what comes next. What comes next in hydrogen NMR is 5 to 6. So what shows up 5 to 6 in hydrogen NMR? An H that's directly attached to an alkene. Yeah, so an H coming off of one of these would be 5 to 6. What shows up 7 to 8? Yeah, a CH on a benzene ring. Once again, a benzene ring, though, is just C double bond Cs in a ring. And so really 5 to 6 and 7 to 8 are hydrogens attached to C double bond Cs. That's kind of your next quartile. Well, that's kind of the same thing as carbon NMR. Carbons in a C double bond C, and in this case, whether they're in an alkene or a benzene ring, would all show up kind of in that next region. See how that's kind of just following the same pattern? All right, so what's farthest to the left on a hydrogen NMR? So an H in a carboxylic acid and an H in this one more functional group. Aldehyde, yeah, in that 9 to 10. Well, farthest to the left on carbon NMR, which is from really 150 up to like 210, is a C double bond O. And so in a hydrogen NMR, it was the H in a carboxylic acid or the H in an aldehyde, but both of those things have carbonyls. So it turns out that the carbonyl containing stuff is farthest to the left in both hydrogen NMR and carbon NMR. And then the carbons in double bonds are kind of that middle left in both hydrogen NMR and carbon NMR. And being next to an O or an N or an X is kind of middle right on both hydrogen NMR and carbon NMR. And then a CH kind of near nothing is farthest to the right, all the way to the right, in both carbon NMR and hydrogen. So while the numbers are the same, the numbers are different in terms of ppm, the rough regions are about the same. And so if you know your hydrogen NMR values already, the numbers aren't precise, but kind of the order in which they go is the same. So hopefully that can save you from feeling like you're memorizing something new, and instead you can associate it to something you know. All right, so when we go through this, you can kind of look at these peaks. You don't have to ask yourself each of these individual questions every time you go through there, but kind of knowing roughly what these quartiles are, we can see that how many carbons are in carbonyls in this specific molecule? Mallory, how many carbons do I have over here? None. How about in the double bond region? Perfect. All right. How many carbons do I have that are right next to an O? None, because there's no peaks between 60 and 90, not even close. So there's no carbons right next to O, none in a triple bond, none attached to nitrogen or halogen. And then lastly, how many of these are just kind of alkanes? 3, because I've got 3 peaks in that just general alkane region. So what we should be looking for is a molecule that has 2 carbons in an alkene and then just 3 carbons that aren't attached to anything, which hopefully makes this pretty simple. This would have carbons next to oxygen, and we don't have that, so it can't be this. This would have 2 different carbons right next to oxygen. We don't have that, so it can't be this. And so this is our answer. We've got 2 different carbon environments, both of which are in the alkene region. And then we have 3 that aren't, that are just kind of alkane. Most of you got that right. Any questions about that? So it's really just 2 things you're looking for in carbon NMR. First, how many peaks do you have, which tells you how many environments. And then secondly, where are they, which kind of tells you what those carbons look like, some information about their environments. And that's all you can get out of carbon NMR. So a lot less information than you get out of hydrogen. All right, any questions on that? We're going to move through and just do some examples for a little while, and then we'll move into hydrogen NMR. Okay, so if you guys printed these out, I sent you a bunch of a handout to print out and bring with you. If you did, great. If you didn't do it, fine. I'm projecting it up on the board, and you can try to follow along. We are going to go through about 5 pages of this today, and then we'll go through the rest of it on Monday. So if you don't have it for today, those of you in Zoom, if you didn't print it out already, print out the same thing and bring it with you on Monday, please. If you did print it out, please bring it with you to whatever version of class you come to on Monday. All right, so this is, again, much like a quiz question. Here is a carbon NMR, and which of these molecules could it potentially be? So kind of a multiple choice question. All right, Miguel, talk us through this.
Okay, we got one that's sort of in the realm of 20, so that looks like it would be like carbon out of the year.
All right, so let's start off with a simpler question. How many carbon environments do I have in this molecule? Right. And sometimes that's all the information you need, but I like what you're doing, so keep going. So you say we have one around 20, which tells us what?
Carbon out of the year.
Okay, good. So this is just, I don't know how you want to write this, but just kind of, I don't know, alkane, carbon. All right?
The next one is between 60 and 70.
Yep.
So that's carbon attached to an alk.
Okay. And that's it. So do you have any alkenes? No. Do you have any carbonyls? So what can you tell me right now?
All the double bond, the that's.
Here, maybe this will help. Yeah, the double bond O, the ketone is right out. All right, so what else can we eliminate? You can do this through process of elimination, or you can find the one you're looking for. Either one is fine. How many environments are present in molecule A?
6.
Yeah,
None of them are identical.
correct.
So that one you can eliminate if you want to.
So if you couldn't hear that in Zoom, there are 6 environments in molecule A, and none of them are identical. And since the NMR says you only have 2 environments, this is right out. That's perfect. So how many environments would be present in this ether right here?
Would that be 2 or would it be more?
Well, let's just kind of start. So let's say this right here is A. I'll do these lowercase letters. Is there any carbon that's exactly the same as this one? Yeah, the one over here, so it's symmetrical. All right, and let's say this one is B. What's exactly the same as B? Yeah. And what about the very end of this? Is it the same as either of those or any of those? Is it the same as A? This one right here?
No, but it also has a form. So
Yeah,
3 environments. No.
exactly. So it's symmetrical, but there's still 3 environments, so there still should be 3 peaks. So if this were your molecule, you would have this one environment that's next to an O, that environment A, and then you'd have 2 of them down in this region. So if this were your molecule, you would expect it to look something like that. Just have a 3rd peak, because you'd have a 3rd environment. But we don't, so that's not there. So that molecule is right out as well. So just by process of elimination, D must be the answer. But to just dig in a little bit, these two carbons are the same. They're both little a. And then all the rest of those are not only symmetrical right and left, but also they're isopropyls, kind of. So those are the same as each other, and then they're symmetrical on the left side. So this one only has two environments. The A's are the carbons in the C single bond O, and then the B is that carbon in the alkane region. So this would be your answer. Does that make sense? So it's kind of like a little logic puzzle, which is great if you like logic puzzles. And if you don't, just know that next Friday we'll be starting on something completely different. Okay. All right, you said you want to try this one? You can, yes, that's great. It's true.
So there are 5 environments.
There are 5 environments.
So that would cross out the first 2.
Yep. So the first molecule here has 6 environments, and the second one has 6 environments. So those are not going to match. Great.
And then the first peak to the left is C attached to L.
Correct. So she said the first peak on the left is a C single bond O. That's a carbon there.
And then I guess the other ones are this out.
Yep. So the rest of these you've got are just kind of alkane.
Would it be third?
Yes, it is. All right, so how do we know it's not this one? Why does this not fit our data?
Would there be a peak like higher up? Closer to like the 60, 90 range?
Yes, exactly. So looking at this molecule right here, you have 2 different carbons that are next to the oxygen. So this one, if this was our molecule, it would have 2 of them, 2 peaks in the 60 to 90 region, and then only 3 peaks down in that alkane region. This one right here only has 1 carbon that's right next to the oxygen, and then it would have A, B, C, D, and there's symmetry of that like split end there. So you would have 4 peaks in the alkane region and 1 in that 60 to 90 region. So that's why this one works. Perfect. Any questions on that? In Zoom, anybody have any questions? Okay, we got one more example for you. This one is has a little bit more stuff going on in terms of functional groups. So Chloe, I'm going to ask you to start this, and then I'm going to interrupt you halfway through, and then I'll let you finish it up. So this is your molecule. What can you tell me based on this right here? Okay, perfect. There are 4 environments. What do you know about those environments? Okay, so kind of alkane or carbons attached to nothing fancy. Right? The one's a carbon attached to oxygen with a single bond. Correct. So this would be a carbon that's double bonded to oxygen. All right, all of that is perfect and good. So hold on for 1 second. There is a crucial tiny piece of information that my guess is you missed when if you're taking notes in the video, which is that this carbon attached to an oxygen is an sp3 carbon attached to an oxygen, which means that it's a carbon making a bunch of single bonds and isn't also involved in a double bond. So to be a little bit more clear on that, if this molecule right here were our answer, which it is not, sorry, you only have 3 to choose from. This carbon right here, which is the carbon of a carboxylic acid, is only 1 carbon. So how many peaks should it give you? It's only 1 carbon. 1. It will only have 1 peak in the carbon NMR. And I know that by looking at this carbon, it is involved in a double bond O, And it is also next to a single bond, but it's still only one carbon. So this carbon right here is going to show up in the 150 to 210 region because it is not an sp3 carbon next to an oxygen. It is a carbon involved in something significantly more de-shielding, that is to say the carbon. In IR, if you had multiple bonds, you would get multiple peaks because IR looks at bonds. But in carbon NMR, you do not get multiple peaks because you're not looking at bonds or anything like that. You're just looking at carbons. And this is only one carbon, so it gives only one peak. So all of these things between 150 and 200, these are carbons in carbonyls. And it might be a ketone. And it might be an aldehyde. And it might be an amide. And it might be an ester. And it might be a carboxylic acid. You don't know, but the thing these all have in common is that they are the carbons in carbonyls, no matter what else is attached to them. Does that make sense? So if you have a carbon in a carbonyl, it's got to be 150 to 210. It doesn't matter if it's also next to an oxygen. So this carbon right here, where do you think it would show up? Way off to the left, correct. So this carbon right here should be in that 150 to 210 region because of the fact that this carbonyl puts it there, even though it's also next to an oxygen. So looking at the data that Chloe just told us about, you do have a carbonyl, a carbon in a carbonyl, and you also have a carbon attached to an oxygen. But because those are two different peaks, those must be two different carbons. So your answer will have a carbon in a carbonyl, no matter what else it has attached, but it'll also have a different carbon that's attached to an O, just by a single bond.
So you're saying it's, oh, okay, right.
So it isn't
So we
this
need another oxygen in the chain there to make.
Yes, so this carbon right here, and whatever this carbon is, we don't know about this carbon and the carbonyl, are different carbons because they have different peaks. All right, Chloe, I'm handing it back to you. Are you ready? I can help you through this if you need it.
Oh, that's good.
You're good?
Oh, that's good.
Okay, so let's go down here. So how many environments does this molecule have? Yeah, perfect. So this would have 4 environments, so that matches. And let's look at our carbons one at a time. We'll just call these little a, little b, little c, and little d. Where would you expect this b to show up? Correct, so that would work. Where would you expect this a to show up? Yeah, far right, so that works too. All right, so looking at C and D, both of those are carbons attached to oxygen. So where would both of those show up? Yeah, in that like 60 to 90 region. So if this were our molecule, then you'd only have one peak off to the far right, which we do, and one peak off to the far left, which we do, but you'd have 2 peaks in the middle here. So basically just one of these would be moved over there. Does that make sense? All right, so that's a right out. Okay. Let's move over here. How many environments does this have? 3. So this can't be right, but let's talk through these a little bit. So we figured it out. We know the right answer, but for this environment A, where would you expect this one to show up? It's both in a double bond O and next to an O. Yeah, so all the way to the left. This environment A should be in the carbonyl region, and you just get one peak over here for environment A. Where would you expect this B to show up? 60 to 90, exactly. So this would be right here. But then because those environment C's are identical, it's only one environment. So it only give you one peak around here. Okay. So which one do you think it is? It definitely is correct. But let's go through and just make sure. So it has 4 environments, A, B, C, and D. So which one goes with which signal? Yep. Right, and we wouldn't know which is which, but that's okay because it doesn't really matter. At least for what we're doing. Yep, B would be in the far left. So even though this carbon B is involved in a double bond O and is next to an O, it's still just a carbonyl, still just one carbon, so all the way to the left. Perfect. And then? Right, exactly. So this one right here, C, that's the one that is next to an oxygen, but it's not in a carbonyl as well, so it just shows up in the next to an oxygen region. How do you feel about that one? Good, great. All right, so those are all of the examples that I want to go through today with you guys. That's about half of our class time. How do you feel about carbon NMR? Can you do this? Should you practice this? Yes, you should practice this. So for Monday, which is just a class period, we're just going to spend Monday practicing. We're going to spend Monday practicing mostly hydrogen NMR and a little bit of carbon NMR, but it's just going to be spectra that you guys interpret. If you look through that packet, it's just spectra for you to interpret. So we're going to spend the rest of today practicing how to interpret hydrogen NMR. But for Monday, there is no new video. In fact, there's not really any new content. It's practicing things that you already kind of know how to do. So what we did for the course of this last week was I gave you information like, I'll just write it right here. You have a peak that integrates to 3H in hydrogen NMR, and it's a triplet, and it's at 1.3 ppm. Tell me what that means, right? So that question is really about one environment. So what we're going to look at today is when you have a full hydrogen NMR. And this is 4 different environments. And so for each one of these, you do this thing. You're going to interpret that signal and tell me what it means about that environment. The difference is, and the new skill set is you need to do that for each of the peaks and then put those puzzle pieces together to make the puzzle, right? I would assume that at some point in their life, everybody in here has done jigsaw puzzles, right? Or some type of puzzles. Okay, people build puzzles in lots of different ways. I like to do puzzles from the inside out. My wife says, that's silly. You should always start with the edges and work your way in. Both of us are capable of completing a jigsaw puzzle, but we approach it in different ways. And you might be thinking right now, you're totally right, or you're totally wrong, but keep your judgment to yourself, I beg of you, because as long as you can get to the right answer, there are a lot of different ways to put pieces together, right? So I don't want to tell you a formalized way that you should go about looking at this and putting the pieces together. But what I will tell you you need to do is you need to be able to look at each of these signals and turn it into a piece. Then how you put pieces together is something that you just need to practice. So I don't have a video telling you how to do that, how to build a puzzle. Instead, we've already learned how to interpret these pieces or these signals, and putting it together is just a matter of practice. So we're going to practice that for the rest of the day. We're going to walk through this one together, and then kind of for the last 15 minutes, I'm going to ask you to do one by yourself. But then I'm going to ask you to save the rest of these problems in this handout, and we'll work through them together as much as we can on Monday. What you do have on Canvas, though, is lots and lots and lots of practice problems about carbon NMRs and hydrogen NMRs and both. I would encourage you to practice the carbon NMR problems from today. Probably they're a little bit more simple and won't take you as long. And then look at Monday stuff and practice those hydrogen NMR problems as well. The only way you're really going to learn how to do this is to practice it. If you didn't pass the interpreting signals quiz, you might want to go back to that and start studying it now, because you really need to be able to do that before you can put pieces together. If your pieces aren't right, this is all going to be a disaster. All right, so this molecule has 4 signals. It also has this thing at 0. This is the little molecule that we add in order to have kind of a blank to have a 0. So this is not a thing you need to interpret. Instead, this molecule right here has 4 peaks, so 4 signals, so 4 hydrogen NMR environments. Yes, we're skipping back to hydrogen NMR. And there's a lot of information. And you can use this information, and I've given you a molecular formula, to figure out the entire structure of the molecule. So let's put it all together in the way that we're used to. This is 1H, and what's the splitting on this guy right here? Yep, so it's a 1H singlet. And you can tell that the chemical shift is at like 2.0 ppm. That information right there is pretty much what we've been using to build environments. All right, this one is 2H. The splitting might be a little bit hard to tell. So what you have up here is a zoomed in version. If you were running this and gathering this data, you would be able to use the computer and just zoom in, and you can tell for sure what it is. So if I give you one of these and it's a little bit hard to tell, I'll give you either a zoom in or I'll just tell you what it is. But if you zoom in, you can see that this is 4 peaks or a quartet. And you can probably tell it's at like 1.4-ish ppm. All right, and we'll call this our environment A and this our environment B. All right, here's our environment C. It is 6 H's, and this is also a singlet. And it's at like 1.1 ppm. And you might not have to write those things down again because you can just look at it and see where they are. What about this one right here? This is our environment D. Yeah, it's a triplet. And you might not be able to make it out very well in here, but there's a zoom in. You can tell this is the zoom in because you can see the chemical shift, 0.7, 0.8, 0.9, so that's clearly right. So this one's pretty low. It's 3H, it's a triplet, and it's around like 0.8 ppm. All right, so those are your signals. You would need to turn each of those into an environment and then put those environments together. So Chloe, you got to go last, so if it's okay, I'm going to skip you, and everybody else is going to get to do an environment. Okay. All right, so let's start at environment A. Miguel, tell me what you know. Actually, let's start at D and go backwards. Tell me what this environment D would be.
All right, so the shift suggests that it's entirely made of like alkanes with no functional groups and no.
Perfect.
So
Yeah, so he just said 0.8 means it's next to nothing really, okay? So let's start with the integral, because that tells you what you are.
3 hydrogens.
Mhm.
3, yeah,
So what is your environment?
3 hydrogen environments.
Nope, it's just 3 hydrogens. So what is it? If you have a 1H, you're usually a CH. If you have 2 H's, you're a CH2. So what's 3? Right, so it itself is a CH3. When you guys were doing your signals, I encouraged you to circle your environment to see what you're looking at. Now it's more important to do that than ever. The reason that we circle this has to do with its neighbors. So this is a triplet. What does a triplet mean? Correct. So what must it be next to? Correct. All right. This environment, D, meaning this peak right here, that's a triplet, is telling you that you are this CH3. It is also telling you you're next to your CH2, but this CH2 is its own environment. So this CH2 will show up somewhere else. So that doesn't mean we have 2 CH2s. It's just that when you're looking at one signal, Miguel, I see you, and I can be talking to you, and you might tell me about your neighbors, but that conversation was between me and you, all right? So even if you tell me that you're sitting next to Yesenia, she'll have her own signal, and so I need to find that signal somewhere else as well. So that's why I think it's really important to circle what you're talking about, you're accounting for, and just know that kind of What you see outside of that circle is your peripheral vision. It helps you to place it, but doesn't account for that CH2. All right, Timothy, tell me about environment C.
It has 6 hydrogens on it,
Correct?
and since it's a single, it means it has no neighbors.
No neighboring
Carbon contained or carbon potential hydrogen.
hydrogens, correct. So there are no hydrogens on neighboring carbons. Okay, but 6 hydrogens, is that a CH6?
No.
No, it's not a CH6. What is it?
Could it be 2 CH3s or
Yes.
3 CH2s?
Yes, it could be 2 CH3s and it could be 3 CH2s. It's pretty unlikely to have symmetrical CH2s. It's far more likely to have symmetrical CH3s. So if you have symmetrical CH2s, you'll probably also have symmetrical CH3s. Because if the middle of a chain is symmetrical, the ends must be symmetrical as well. All right. So when you see a 6H peak, it's almost always going to be 2 CH3s. All right. So does that seem reasonable, 2 CH3s? Tell me about what they're connected to, though. Because they've got to be connected to something.
And the 1.1, I think G would be like attached to the CH2 over there. Or,
Well, they can't be next to the CH2 because they
No,
don't have any hydrogen neighbors, right?
right.
Okay, so let's real quick look at what we have in this molecule. There's only 3 things. There's carbons, hydrogens, and oxygens. Can there be a hydrogen that they're attached to?
No.
No, because then they'd be CH4s, and they're methane, and they're floating in the room, right? Can they be oxygen?
Yes.
If you were a CH3 next to an oxygen, where would you show up? Chemical shift-wise.
Shows 3 to 4.
3 to 4 ppm, and this peak is at 1.1. So can they be next to oxygens?
No.
No. So what's left?
Carbon?
Yes. So they must be next to a carbon. Does that make sense? Because there's nothing else they could be next to. And what can you tell me about that carbon?
You either have carbons or oxygens attached.
Right. That carbon has no H's.
No way.
Everybody go with that? All right. So I'm going to write that. No H's. And that is what you know about those CH3s. They're both attached to some carbon that has no H's. Any questions on that or how we figured that out? Hopefully this is ringing bells. It should be a lot like your quiz on Wednesday. All right. The good news is that I'm trying to help you get every piece of information. If you don't get every piece of information, you can still probably put this together. So even if you, because these all have to fit, a lot of times, if there's one you just can't figure out, you can build a molecule just based on everything else. All right, so that's environment D and C. All right, now are you ready? All right, tell me about B.
B has 2 hydrogens.
Yes?
so it's probably CH2.
That's definitely a CH2.
And it's a quartet, so there's 3 neighboring hydrogens.
Correct, she said it's a quartet, so there's 3 neighboring hydrogens. So 3 neighboring hydrogens could be a couple different things. So what could it be? Okay, so it could be a CH and a CH2 if this was in a bubble, but it's not in a bubble. You see all of its other possible neighbors. So for this to be a CH2 next to both a CH2 and a CH, you'd need to have another environment that integrates to 1 to be a CH. And we do have something that integrates to 1, but you'd also have to have a CH2 next door. Do you have any other peaks that integrate to 2? No, so you can't be next to a CH and a CH2. So it has to be next to a CH3. And we kind of knew there was a CH2 next to a CH3 because we already knew there was a CH3 next to a CH2. And if these two are neighbors, well, they're still neighbors from the other neighbor's point of view. All right, so if that CH2 is next to a CH3 on one side, what must be over here?
Probably
Probably a carbon is true.
because the oxygen would
Exactly. So much like we did a second ago, if there were an oxygen over here, the CH2 would be in the 3 to 4 region. If this were a hydrogen, it would end the molecule. So it must be a carbon, but because you were a quartet and all of your hydrogens were over here on the left side, what do you know about this carbon here? Perfect. That one also has no H's. All right, someone draw a logical conclusion for me right now. That mystery C with no H's is probably the same C with no H's in both of those, right? Does that make sense? They're probably next to the same carbon with no H's. I mean, you only have 5 carbons in the molecule. You can't have like a bunch of different carbons with no H's. All right, we'll put this together in a minute. I'm getting ahead of myself. All right, let's skip to this one. Yesenia, you've got the trickiest one here. Uh-huh. Well, there is no evidence of a double bond in this molecule, which is making this weird. All right, this is tricky, but I really want it not to be. I kind of railed on this a little bit the last time we had class, which was Monday. If you have a 1H singlet, it's almost always, nope. So 1H singlet way down here on the right side of the NMR is almost just always an OH or an NH. Because it's possible for it to be a CH, but it's a really, really, really weird situation. Because for it to have no neighbors and be a CH, it would mean that all of its neighbors have no neighboring hydrogens. So it's just like this huge web of carbons just attached to carbons, which is pretty unlikely. Far more likely, if you have a 1H singlet, it's either an OH or an NH. And in this molecule, there are no nitrogens, so probably doesn't OH. So these are my pieces, and I have to put them together. You can start anywhere you want. You can if you want to. No, I was just saying you can start anywhere you want. You can start with at the edges, or you can start in the middle, or you can just start with things that you can tell definitely aren't right next to each other. I will do this one if you don't mind, unless anyone would like to jump in. If you want to do it yourself, feel free to just ignore me and put it together. That's fine. I like to start as close to the middle as possible. Again, that's just a matter of personal preference. But this chunk right here gives me the most information about neighbors. So this is where I would start. But you can start anywhere you want. Probably a lot of people would like to start at this one because that's a CH3 and you can build inwards. But if I were to start right here, which I will do, then I'm going to rewrite this thing. I've got a CH2 that I know is next to a carbon with no H's and is next to a CH3. And this was my environment B right here. So I have accounted for that. So I'm going to cross this one out. Done. Check. Well, the CH3 that was next to a CH2, this one right here, must be environment D, because environment D was a CH3 next to a CH2. So this one right here that I'm circling there, that's environment D. And now I can cross that one out. So the only things left are an OH and 2 CH3s that are identical in terms of environments, but they're still 2 different CH3s. And they're both attached to a carbon with no hydrogens. Well, they must be attached to this carbon with no hydrogens because I'm kind of running out of parts. So 2 of these bonds right here must be to those 2 CH3s. And those are both my environment C, because that was 2 CH3s attached to a carbon with no H's. And then the only thing left I have is a bond to something. And I don't really know what that something is besides that it's not a hydrogen. Well, the only thing I have left unaccounted for is this OH. So that OH must just be right here. And that is a full molecule with no hanging bonds to nothing. All of your hydrogens make 1 bond, all of your carbons make 4 bonds, your oxygen makes 2 bonds, and it accounts for 5 carbons 1, 2, 3, 4, 5. 1 oxygen, check. And then if we wanted to, we could add up all our hydrogens and you got 12. Any questions? Yes.
That's a stupid question. How would we know that the OH is there, not like the CH3 side? Or does it not matter?
So where else did we have a bond to put anything? So over here on the right side, by the way, this is, you could choose wherever you wanted to put the CH3s because this is going to be a 3-dimensional structure so it can rotate. So
Remember all that.
yeah. So if you put the OH here or here and put the CH3s up there or top and bottom, it's still the same molecule. So how do you feel? So this is all stuff we did before. What we did do is just put them together. All right, we've got about 15 minutes. I want to give you guys about 10 minutes to try this yourselves, and then we'll spend about 5 minutes putting it together. But I will give you a couple warnings before you get started. This peak way off to the left here that says 1H, there's an expansion, but the expansion isn't still super helpful, I don't think. If you count them, there are 6 peaks in there. I'm just gonna write that right here. There are 6 peaks. This is another 1H singlet, and a 1H singlet is most likely something. Furthermore, it's broad. You see that kind of broad chunk? For a singlet, that tells us the same thing. Okay, here's our biggest problem. This peak here that's 4 H's, no matter how well you zoom in, this is an indecipherable mess. And the reason for that is that unfortunately, there are 2 environments that are stuck on top of each other. And so this is some signal stuck on top of another signal. So you cannot do anything to tease those apart. So what you have to do is build the rest of this molecule and figure it out by deduction. I will tell you that this is 2 different CH2s. But to save those for the end, because you can't start from those since you don't know what their splitting is, because it's a mess. Sorry. And then this thing right here, this is 3H. Can you tell what the splitting is there? Yep, so this is a doublet. And then this one, can you tell what that is? Ping, ping, ping. It is a triple. All right, and then ignore that, that's your 0 thing. So you have A, B, this is C and D, E and F. So interpret A and B and E and F, and using those, you'll be able to put the molecule together. If you have questions, you can ask me. Otherwise, I'm going to give you about 8 minutes now, and then we'll work on it together. If you all in Zoom have any questions, I'm right here. I can hear you even if I'm walking around. Because it's a quartet, which means it has to be inhabitants. So it could be like a CH2 and CH, except that we don't have any CH2 next to it. So it has to be next to a CH3 because that's like that. And if all the hydrogens are there, they can't be. So it's lots and lots of tiny little. You're welcome. How's it going? You don't have any nitrogens, so it's got to be chemical shift is a little bit. All right, 2 more minutes and we'll start going through this together. You will have more than 8 minutes to do these. Your piece for A is perfect and has told you most of it's not good. This is really good. So here's the only thing that's necessary. So that's CH3, right, that has 2 hydrogen figures. But I can only have 1 carbon figure. It's really close, it's got 5 bonds. So everything else about it is perfect. But one of those CHs can't exist. Your A is great. It's in that 3 to 4 region though, so it isn't good. Yeah, so instead of a C there. Yeah, perfect, perfect. All right, it is 1:55. Let's put this together. If you are still working on it and you feel like you got a good hold on what's going on, feel free to ignore me and just keep working on it on your own, and we'll get the answer up here eventually. Chloe, I am going to ask you one question. Do you want to start in the middle or on the outside? Okay, in the middle. So what is normally on the outside, if that's your comfort zone? The outside is probably going to be CH3s, because CH3s are always going to be, if they exist, that's what's at the end of the chain. So the part of this that is the most central to the molecule would be something with a whole lot of splitting. And the thing with the most splitting is this environment A right here. So this is a 1H, but it's not a singlet. A 1H singlet is what's usually an OH or an NH. And since we don't have any nitrogens, this environment B right here must be, I'll do this in a different color. This guy, oh dear. Environment B must be an OH. But this environment A, that's a 1H with 6 peaks, that's got to be a CH. Because OHs don't split, so they don't ever have peaks like that. So what we can tell from this one, you want to do this one? You did it, right? So it is a CH. What can you tell me that it's next to? Yeah, it's got to have 5 hydrogen neighbors. There's a lot of different ways of having 5 hydrogen neighbors until you look at the chemical shift. And since it's between 3 and 4 ppm, what do you know about its neighbor? Right, it's got to have an oxygen next door. So technically O or N or X, but we know that the molecule doesn't have any nitrogens or halogens, so it's got to be next to an O. Right, and now, because we've got an oxygen on one of those sides, you got to have your 5 hydrogen neighbors on these 2 spots. So what must those 2 spots be? Perfect, a CH3 and a CH2. All right, and so this is our environment A, check. Our environment B is our OH. Well, here's the O, so that must have an H, and that must be B, check. And then, so here's a different way of approaching it. Instead of doing each of these individually, let's try to find what we know to be there. Well, if this CH is next to a CH3, there must be a CH3 out here that's next to a CH. So if you're the CH3 next to the CH, what would your splitting be? You only have 1 hydrogen neighbor. Doublet. So this should be a 3H doublet. And here is our 3H doublet. So this right here, must be environment E. So we have checked off 3 of our 4 doable peaks already. And where we are right now is we've got a CH2, but we can't do anything with that because the CH2 is down in here. Since the splitting is unclear, we can't say for sure what's next door. So we're kind of at a little bit of a muddy dead end. That doesn't mean we're finished. It just means that we can't keep going yet. So A we're good with, B we're good with, E we're good with, C and D we can't do much about. So that just leaves us F. F is 3H, so it must be a CH3. It's got to be over here somewhere. And it's a triplet. If you have a triplet, what's next door? A CH2. Okay. So we have now accounted for A and B and E and F. And all that's left is we've got 4 hydrogens. And we can tell that that's got to be 2 different CH2s because you can't have a CH4. And up here, what we've drawn based on our neighbors is we've found our 2 CH2s. And so this is our C and our D. And you don't know which one is which, but it doesn't really matter because they're both CH2s and they've got to be attached to each other. So you had the left side of the molecule and you kind of ran into a muddy dead end. And then you got the right side of the molecule and you ran into a muddy end. But you hadn't done anything else with the molecule, so they just had to be attached to each other. And that was how we could put this together. So the reason that this happens is because if you think about where this is, it's 1 to 1.5, and where this is, it's 1 to 1.5. So both of these peaks, these are different, but they're both in the 1 to 1.5 region. And it turned out they showed up at about 1.4 and 1.4. And that's just kind of bad luck, but it happens. This one right here would have 5 hydrogen neighbors, so it should be 6 peaks. This one would have 3 hydrogen neighbors, so it should be 4 peaks. So this is a 4-peak and 6-peak signal that are almost but not exactly identical, that just kind of show up each other, and that just ended up being this. And you can't do much about that, and sometimes that happens. All right, any questions on this? All right, I got one last question for you for the week. Should you practice this? Yes, thanks, enjoy. Do some puzzles this weekend. As a reminder, don't finish up this problem set. We will work through these together in class on Monday. Go through the problem sets that are on ThinkCanvas site for problems, practice problems. Thanks, have a lovely weekend. I will see you all sometime next week.